Great. Thank you very much for the introduction, and thank you for having me as well. It's really great to be invited to talk about my work. So yeah, I'll talk today about Eigenstate thermalization and how this can be seen from a framework of chaotic eigenstates. So the key questions and the key kind of motivations behind this work are the question of how statistical physics can be seen to emerge from unitary quantum dynamics. So a typical picture here that we might look at is some system initialized in some pure state of, let's say, some lattice or a spin train, for example. And then we evolve the system under some generic non-integrable Hamiltonian for some time under unitary dynamics of this global system. And then for some local observable of the system, what one expects from statistical physics is that after some thermalization time, we have that the expectation value of some local observable is at least approximately equal to a microcanonical or thermal ensemble. So the key question really underpinning statistical physics in a sense is under what conditions can we see that this type of phenomena will occur. A further question that I'll be looking at is asking the question of when this sort of behavior can be seen to be equivalent to classical Brownian dynamics. So when does unitary quantum dynamics start to look like this Brownian motion? So a canonical example here is the Ornstein-Uhlenbeck process, which is simply a Brownian particle in a harmonic trap. So we'll be making this comparison later on as well. A third important question that we'll be looking at is for the formulation that we developed to describe quantum thermalization, can we exploit this formalism to find useful procedures of characterizing quantum devices? So, for example, we'll look at a protocol for measuring the density of states and an effective Hilbert space dimension that are based upon the theory that we'll outline. So just for a quick outline, I'll start with looking at generic properties of chaotic quantum systems, and then describe how these properties can be exploited to develop a method for making analytical calculations, and then look at these applications to quantum devices, and finally, the emergence of classicality in the systems. So starting with some generic properties of chaotic quantum systems, I'll start with ETH, and this won't be an assumption that I make later, but it would be amiss to not describe it, because this ETH really underpins a lot of the modern understanding of thermalization. So we'll look to be deriving this from the assumptions that we'll make later. So the first part here is the diagonal part.
Sorry to interrupt you there, Charlie, but I mean, it seems that your sound is a little bit muffled. I don't know if it's your earphones, but maybe you could improve it if we...
Let me just try and...
Is that any better?
That's a bit better. I mean, the microphone seems to be up a little bit loud, but okay, I mean...
Okay. So I can just move a little bit further back. Is that all right?
Yeah, it's a bit loud, I would say. You know, the sound is coming. I mean, maybe it's the mic setting.
So I can go on Zoom if I.
Any ideas there from the crowd of on? Yeah.
Okay, yeah, I've got mic settings for Zoom. I can't control them now. I can't control them.
You can control them in Zoom. I mean, if you have to unclick automatically adjust microphone volume.
Oh, there we go. That's why it's not.
If you go, yeah, and then you can control them.
Yeah.
Okay. Is that better? Let's turn down a bit.
Yeah, I'd say that's good.
A bit better. Yeah, it was weird before. Yeah.
It was making a slightly annoying noise, but now it's right. Much better. Yeah.
Yeah. Perfect. Okay. Right. Yeah. Just obviously interrupt again if there's any more problems like that. So just turn this laser pointer back on. Okay. Cool. So yeah, for the first part of the ETH, we have the important part is essentially that this is some smooth function, and that's of the energy that's the energy of the eigenstate. And this smooth function is equal to the microcanonical average at that energy. And it's essentially from this that we get the words eigenstate thermalization, in the sense that the eigenstate expectation value of the observable is equal to the thermal expectation value. And it's this term that dictates the long time average of the observable. So the fulfillment of this term of the ETH guarantees that under some reasonable assumptions, that the long time average of your observable is equal to the microcanonical average. And for the second part, we have essentially what's important is that this term is small, and this R mu nu is some stochastic variable. And we have the density of states occurring here, dV, and this is some smooth function that decays with the energy difference between omega, between the energies of the eigenstates. But the important point here is that this term guarantees that the fluctuations around this microcanonical average are small. So between these two terms, we guarantee thermalization in the sense that we have a decay to a thermal equilibrium and small fluctuations around it. So what we would like on top of this essentially is that this is a very strong assumption to be making a priori, and it tells us nothing about the particular underlying mechanism behind it, or which observables that this should apply to. And particularly interesting, I think, and what will be the main focus is that this tells us nothing in particular about the dynamics to equilibrium or the timescales of equilibration. So these are some additional motivations in the context of the ETH. So the main assumption that I'll be making is that of chaotic wave functions. And this can essentially be understood as a coarse graining of the eigenstates psi mu, which are the eigenstates of the full many-body chaotic Hamiltonian, when expressed in terms of some non-interacting Hamiltonian. And the ansatz is that this coarse graining gives an essentially Gaussian probability distribution. That's Gaussian up to a point, and that's this interaction term, or this effective interaction term in the statistical theory, that simply guarantees the mutual orthogonality of the individual eigenstates. So this is kind of the minimum interaction possible in such systems. So we're assuming no additional symmetries, essentially. So just to convince you that this is a good description of chaotic systems, we've got here just a coarse-grained eigenstate. Sorry? No, okay.
Sorry, I think he just had a mute. But now that you're interrupted, anyway, maybe can I ask just to make sure I understand it? So the basis you're expanding in, Charlie, this is like, so an example would be, you know, the computational basis, or would it be the non-interacting fermion basis? Say, for example, if you had XXZ chain, would you be expanding in the basis of the XY model or the basis of the Z term?
So you take the part that you're looking at where your local observable is, and in the basis where you have the entire Hamiltonian, except that part is disconnected.
I see.
So let's say you have some local observable on one site and coupling between that site and the rest of the system that acts as the bath. So generally this will be you're just removing that interaction and expanding.
This is what sometimes they call mean field basis or something like this.
Yeah,
okay.
Precisely. Yeah, the mean field basis would be exactly what. Yes. So this gives a good description of this. This is just a spin chain in a non-integrable limit, and more generally, what we see is that this occurs as. So this is where I'm going from A, B, C to D here. Is increasing the strength of a integrability breaking perturbation, and we see that this Gaussian probability distribution arises concurrently with what's more generally used as a marker of quantum chaos, which is the energy level statistics, or the energy gap statistics. Sorry. So these energy gaps between the energy levels move from a Poissonian statistics in the integrable regime to Wigner-Dyson statistics in the non-integrable regime, or in the chaotic regime. So these can be seen as at least numerically they occur concurrently. And the latter, this Wigner-Dyson statistics, is precisely the statistics of random matrices. And further, we expect this Gaussian probability distribution to be reasonable for random matrices as well. So that brings us on to the random matrix model that we'll be using as a kind of heuristic for the many-body quantum system. Though I'll stress that the ansatz here is more general than a specific random matrix model, so it could be applied to other random matrix models as well. And in the context of a random matrix model, the probability distribution is taken over the ensemble of random matrices, whereas applied to a single instance of a realistic system, this should be thought of instead of as a coarse graining. And this kind of picture is that these two are somewhat equivalent. So the specific random matrix model we'll be using was introduced by Deutsch in the early 90s in one of the pioneering papers looking at the ETH, or what's now known as the ETH. And it consists of a linear distribution of energy levels separated by some energy gap omega naught. And these energy levels are then all coupled together by the random matrix. So this part H naught has no random component, and then we have some effective coupling strength G that couples all these energies together randomly. And so this model can be solved using this chaotic wave function ansatz, this like nearly Gaussian probability distribution. And what we find is that lambda, which is the function that acts as the kind of envelope of the chaotic wave functions, can be expressed as a Lorentzian distribution with this width gamma, which is proportional to the coupling strength here, G. So we have here the kind of first hints at eigenstate thermalization from this model, in the sense that this envelope of the eigenstates themselves form this kind of effective microcanonical ensemble, in the sense that they're defined over some width around some central energy. And it's this that becomes the kind of main mechanism for the diagonal part, at least, of the ETH. So a further property of this model, and that's as well a property of generically of the chaotic wave function ansatz, is this self-averaging property. So this can be understood as essentially the single instance of a realization of this random matrix model is indistinguishable from taking the ensemble average of the model. And this can be understood in the context of the coarse graining by the coarse grained description is equivalent to the fine grained description. And this is analytically checked by showing that this variance tends to 0 in the large n limit. And this is shown exactly as a consequence of the chaotic wave functions, and not for the specific random matrix model. So it's independent of the specific model. And also, importantly, it's valid for a given non-equilibrium initial state. So there's no requirement of making an average over initial states here, like lots of random matrix models have to do. This isn't limited, for example, to infinite temperature. It's for a given initial state. So some additional assumptions are that we'll use local observables, which implies a sparsity condition. I'll just quickly explain. Which so essentially we have that the matrix elements in this non-interacting basis, so where we have the system and the bath as the eigenstates of the non-interacting basis, so these product states of the system and the bath. In this basis, the observables have this very simple form, where they're proportional to the identity on the bath Hilbert space. And what this leads to is essentially a simplification of lots of summations, where we have this effective sparsity in this basis, and it's also of a particularly simple form, where there's this additional sum introduced that reduces one of the summations, and this sum is essentially over all of the possible transitions that can be made by an action of that observable. So summarizing, essentially, these observables are sparse and simple in a specific basis. And a second assumption that we make is a bit more technical, but it essentially boils down to the smoothness of a microcanonical average. And so we make approximations on summations that look like this. What this boils down to is the ability to define some microcanonical average that we write here with this notation, and this average should vary slowly over the width gamma of a single eigenstate. So this is, yeah, essentially the assumption is that we want to be able to define this microcanonical average. And finally, for this section, we'll ask how does this random matrix model apply to a realistic many-body system? So the key assumption in making this heuristic kind of comparison between the random matrix theory and a chaotic quantum system is that the interaction Hamiltonian in this basis, in this mean field basis, or the non-interacting basis, looks a lot like a random matrix. So it's the specific basis where we see the matrix, and it can be seen quite easily by just expressing this, that this isn't exactly correct, right? So what we have is local interactions that limit the range over which this looks like a random matrix. So what this essentially does is limits the applicability of the random matrix model to the specific regime where gamma, which is again the width of the single eigenstates, is smaller than this width of some effective kind of density of states that defines the energies over which this system looks random. So if this coupling is smaller than this energy, locally at any given energy, the Hamiltonian will look like a random matrix. And this is where we expect the random matrix model to be a good heuristic, though outside of this regime, the chaotic wave function ansatz should still apply. And what would change is that you would have some different function lambda. It wouldn't be a Lorentzian anymore. So for example, numerically, you can find in a strongly coupled spin chain, it instead resembles a Gaussian. And though that part we haven't derived analytically. But what making this comparison also allows us to do is calculate the value of gamma from this picture, just by essentially zooming in here, treating it as a random matrix, and going back to the random matrix theory equation and calculating this value. So this allows us to apply the heuristic of the random matrix model without using a fit to the time dependence or the eigenstates or something like that. So now to try and put these parts together and discuss how we can actually use these to make calculations of useful quantities. So the key building block, essentially, of these calculations will be the correlation functions of the system, which we build again from this probability distribution, from the kind of typical method that involving successive derivatives of a partition function that we build from this probability distribution. And what we find is that the correlation functions, what one would expect for a purely Gaussian theory, is that there's only 2-point correlation functions. That we see that the effect of this effective interaction is to introduce a non-trivial 4-point correlation function. So essentially, just to make this explicit, the 2-point correlation functions of just the Gaussian part are just a product of these lambda functions that are the eigenstate envelopes. And then the contribution, or due to this orthogonality component, is a bit more complicated, but again can be expressed in terms of these lambda functions. So if you know these lambda functions, you can essentially make the calculation as long as you can perform the integrals. So we have this non-trivial 4-point correlation function that we'll see is very important for having consistent results in the end. So then, given these correlation functions, we can develop a kind of recipe for making these calculations. So I'll use an example here as the time dependence of some observable, which the first step is to rewrite this so that the observable is in the non-interacting basis. And this involves including these coefficients of the eigenstates and some additional coefficients that describe your initial state. So the next step then is by making use of this self-averaging condition, or the self-averaging property of the chaotic wave functions, we can replace this string of eigenstate coefficients with the ensemble average, or the coarse-grained version, or this correlation function, importantly. And finally, we can then exploit these smoothness and locality conditions that allow us to turn these summations into integrals and perform the integrals over the functions lambda that are now Lorentzians, and at least with the random matrix theory, they're Lorentzian distributions, and they're quite simple to perform the calculations. So for the first example here, we will calculate the ETH, and the diagonal part here was already done in the early 90s by Deutsch, and we see quite simply here that it gives some smooth function of the energy, which is equal to a microcanonical average, right? So this function lambda just picks out the elements O alpha alpha around the energy E mu with some width lambda. So this is precisely a microcanonical average and gives us that first term in the ETH. And then the second term is a little bit more complicated in the sense that if we were to take just the ensemble average and look at the off-diagonal matrix elements, these would average to 0. So we take the square, the absolute value squared, and this gives us a 4-point correlation function that we integrate over. And what we see is we find that we can essentially calculate this function f that is in the second term of the ETH, and this turns out to be, at least for the Lorentzian lambda, gives us a Lorentzian distribution with twice the width of the eigenstate. And additionally, you see this factor here of omega naught, which is 1 over the density of states. So we get the correct scaling as well that's implied by the ETH. And again, this can be generalized for different functions lambda that describe the envelope of the chaotic wave functions. It's just for the random matrix model that they're Lorentzian. So the summary here is that the ETH can be derived from 3 simpler assumptions that are chaotic wave functions, the restriction to local or k-local observables, and this smoothness assumption. And so to convince you it's a good description still of the picture of this random matrix model, is the comparison to a spin chain. And the important part here is not the specific Hamiltonian, it's that it's non-integrable and doesn't have any specific symmetries, so that we can, at the coarse-grained level, get a very good fit to the Lorentzian distribution of both the eigenstate envelopes and this observable envelope. And these we do find to be pretty much exactly twice the width as predicted by the random matrix model. And again, using that method that we showed before by looking at the interaction Hamiltonian of the spin chain in the non-interacting basis, we can actually calculate the width of these eigenstates from this without having to diagonalize the Hamiltonian first. So it's essentially numerically as difficult, but it's a good check that the theory is predicting the right thing. So the second example we'll look at is the dynamics of the observables that I looked at quickly earlier before, and following that same recipe as was outlined, what we obtain is this description of the decay to equilibrium. So we have this exponential decay at the rate given by 2 gamma, and this essentially comes from the Fourier transform of the Lorentzian that describes the observable. We have some component that describes the free evolution under the non-interacting Hamiltonian, and then these factors dictate the equilibrium value. And I'll stress here that this orthogonality condition can be seen explicitly here in the sense that if we ignore it, the long time average won't make sense. We can never get the correct long time average if we ignore this orthogonality condition. I think this is kind of intuitively quite a surprising result, that just this what you'd think of as a very weak interaction due to just the mutual orthogonality of eigenstates is actually this vital to the long time dynamics of a system. So again, comparing to this spin chain, and again we'll cover up the Barth Hamiltonian because it's not particularly important here. It's just that it generates this universal dynamics in the chaotic regime. We see a good fit to that's what's predicted by this random matrix theory. And I'm keeping here this system part of the Hamiltonian, because if I go back here, this is precisely what dictates this part of the equation. So this system part of the Hamiltonian gives us this procession of observables, and this occurs when the observable doesn't commute with the system Hamiltonian.
Charlie, can I ask a question? I mean, so I'm trying to figure out with this random matrix model. So, I mean, usually in ETH, the sort of energy of the initial state sets the temperature that you equilibrate to. So,
yeah,
where is this in the structure actually? I mean, where do I see varying the temperature here? I mean,
okay, yeah, this doesn't show up yet, but when I talk later about Brownian motion, then we'll see the temperature arise explicitly.
Because I mean, always the criticism of random matrix theory is somehow that, you know, you don't have an energy dependence explicitly there. It somehow replicates infinite temperature, but not really sort of finite temperature as well. But I'm just trying to, maybe I'm a bit confused about what the
yeah, so this is a common downfall of lots of random matrix models, but we don't fall into it here because we're able to specifically like dictate what the initial state is. So here I'm looking at initial pure states, and we'll see that this does have a description in terms of a finite temperature of the system.
But what is the density of states actually? I mean, what is the density of states in this random? Because usually, I mean, with you know, it's some sort of semicircular distribution for GOE, but here it must be different, right?
Yeah, here essentially it's the inverse of this energy spacing omega naught.
Right.
So with it, and what we require is only that the random matrix theory works within the width of a single eigenstate. And this means that the density of states can change as long as it changes over a small enough, as long as it's smooth over this width.
It seems subtle, but anyway, I mean, I'll think about it. Okay, thanks.
Sorry, can I ask, just because I'm also, this is a really interesting point. I mean, what you said, it sounds like you have a kind of almost a different random matrix model for each initial state, right? I mean, somehow it changes with the energy. Is that a fair thing to say? Okay, thanks. That clarifies it, I think.
Yeah, precisely. I think we have, yeah, exactly. For each different energy initial state, it's a different random matrix model. And so even
in the original sort of Deutsch 91 paper, I mean, there it's not like that, right? It is not like that. Or is it exactly? I mean,
no, it's not. It's not like that.
No.
Yeah. So.
Yeah.
I mean,
no. They don't.
Sorry, Charlie, but I mean, it seems that like what Mark said is true. So, I mean, you're saying that what this mathematical construction, this random matrix theory you have is sort of agrees with the sort of ETH sort of prediction, at least within these assumptions, right? Is that what you're saying?
Yeah. Yeah. So we have here for multiple different initial states. These are different product states, and these are eigenstates of the non-interacting Hamiltonian. And this is just a more generic product state. And for different observables, so we get this precession when the observable doesn't commute with the system Hamiltonian. So the third example I'll discuss is this of the observable fluctuations, which are dictated again by the second term of the ETH. And there are, at least these time fluctuations are. So it's because there are two potential types of fluctuations that we'll look at, and the first is these time fluctuations that are the relevant ones for thermalization, and that these are the ones that we expect to be exponentially small in the size of the system plus bath. So these describe the equilibration of the system. And the second type of fluctuations that we'll look at later are the quantum fluctuations, which are simply the variance of the observable at a given time, which is more the difference in what you expect to measure upon repeated measurements at the same time. So, and it's this that we'll see is relevant for the comparison to Brownian motion. And this can be calculated very trivially from the last example, in the sense that we already have these time dependence of observables. So in the long time limit where we'll be interested for Brownian motion, it's just given by this microcanonical variance. So the time fluctuations can be written like this, assuming non-degenerate energy gaps, and applying that same recipe as before, using the self-averaging assumption. What we obtain is this result where these fluctuations decay with the density of states, and this is the density of states taken at the energy of the initial state, and also have this factor of the decay rate, or the width of the eigenstate here. So this resembles a sort of fluctuation dissipation theorem, in the sense that we have the long time fluctuations given in terms of a decay rate. And again, we see that this does match what we obtain numerically for a quantum spin chain in the chaotic regime. So it checks out numerically.
Sorry, Charlie, I'm sorry to interrupt you, but I'm really trying to understand everything. I mean, so gamma is the width of the initial distribution of the state. That
it's the width of the eigenstates of the system. So you have some, let's say you have an initial eigenstate of H0, and then the action of the perturbation of the interaction Hamiltonian kind of spreads these eigenstates out by some amount.
I see.
And
It's yeah, okay. I understand. It's like a local density of states or something like this.
Yeah. It's very much like a local density of states. People call it a strength, or a similar thing to strength.
Okay. Yeah, then I know the strength function. Okay, perfect.
Yeah.
Okay. Thanks.
So it's the width of that. And I've been calling it the eigenstate envelope, but it's a very it's all the same thing really, or very similar.
And that sort of sorry, I mean that thing is directly, like, it's proportional to the level of interaction in your system. Is that right?
Yeah. So this is gamma is proportional to G squared, and G is the prefactor for the random matrix coupling. So I'll just a comment on the calculation of these fluctuations is that they actually require larger correlation functions again, in a sense, because when we expand this equation out fully to write the observables in the non-interacting basis, this becomes an 8-point correlation function, right? So you take the correlation function around here, and then so in practice we then need to use a kind of method of contractions to contract the indices to reduce this to the sum of 4-point correlation functions, which are the biggest non-trivial kind of building block of the correlation functions within this model. And then we can use the sparsity condition on these observable matrix elements that arises again from the locality of these observables, or they can also be k-local and even on all of the sites, but this sparsity requires that there's this kind of k-local structure, and this significantly reduces the number of contributions to this summation. So it ends up with a like manageable number of correlation functions that you actually have to calculate. So this approach means that more complicated things are obtainable within this theory. So we can get autocorrelation functions and potentially even the out-of-time order correlator, which is a 12-point correlation function, but with enough patience, it's doable, and you can get these larger things. So I'm I'll talk about a couple of applications to quantum devices. So the first one is quite a simple consequence of two of the results that we've already seen, which are the long time limits of both of these types of fluctuations. And the ratio of these turns out to be proportional simply to the density of states times gamma. So essentially what we have now is three measurable quantities: the fluctuation, or the quantum fluctuations, the long time fluctuations, and gamma, which is the decay rate of the system as well, which give us access to the density of states at the energy of the initial state. So this is a numerical check on a spin chain where these yellow dots are calculated from a direct exact diagonalization, and blue as well from exact diagonalization, but exploiting this fluctuation theorem to find this result. So we see that this works, and particularly well for larger n, as we would expect it to look more like a random matrix in that limit. So yeah, the crux is that we could estimate the density of states from simply the dynamics of thermalization in such a system. And the second application that we've got to a quantum device is more of a specific setup where we restrict to the specific case of looking at the system, which is a single qubit with a zero Hamiltonian, so there's no bias on the energies, and then look at the device in an initial infinite temperature state. And this device acts as our bath, and it's essentially the thing that we want to characterize.
So sorry, Charlie. I mean, why are you taking the identity there? I mean, can you not just take? I mean, am I missing something here? I mean, why are you not taking eigenstate there? I mean,
oh, we could within the theory, yeah. This is more just a specific application that we're thinking of.
Fine. Okay, so you could take a high-lying energy eigenstate of something generic.
We would actually see something in that case that would be slightly different, because what the result of taking this infinite temperature state here gives us a slightly different form of the fluctuation dissipation relation here. And what occurs is essentially that because of this additional averaging that is done by the infinite temperature state, we have this additional factor that occurs on the denominator of this of the fluctuations that scales with the effect of an effective Hilbert space dimension. So what this number essentially is the number of eigenstates of the bath that contribute to the dynamics of the probe. And again, this can be expressed in terms of like measurable or calculable quantities. So we have C, which is some constant that is trivially obtainable from the observable, and this is the average density of states over all energies. So it's also very, very simple. For, say, a qubit, it's 2 to the m. So also a spin of a chain of qubits is 2 to the m. So what the initial state, being an infinite temperature state, does here is add this component here. And actually, if it's a thermal state, you get the purity of that state, right? So this on the bottom. So it kind of scales with the number of eigenstates that contribute to this dynamics. So what we would expect for a chain of qubits is that this number would scale exponentially with system size with some constant, and that constant for fully connected qubits, if they were all equally contributing, would be ln2. So that this effective Hilbert space dimension would just be 2 to the n. However, for this locally connected spin chain, we observe that this still scales exponentially, as we would expect, but is a slightly lower value due to the local connectivity of the sites. But again, the key point is that this constant, this value, is obtainable from measurable quantities of the thermalization process, albeit more difficult in this case because this is a very big number and it makes the fluctuations much smaller and harder to measure. Though this can give us some estimate of the effective Hilbert space dimension of the model. So that's yeah, I'll now move on to the last part, which is the emergent classicality, and it's here that we'll start to look at how we get this effective temperature. So the key question is, when in this thermalization dynamics that we can describe from this chaotic wave function regime, we want to look for when markers of classicality emerge. And in particular, how does a global pure state of the total system plus bath lead to an effective temperature for the system? And to do this, we'll look at like classical observables that we define in the sense that we're just limiting now to observables that are diagonal in the system basis. So in the basis of the non-interacting Hamiltonian. So that's the additional restriction we'll make here. And to start with, we'll look at now the trajectories that we obtain under repeated measurements of these observables on the system. So in this case, what we essentially see is the thermalization processes. We're looking at the thermalization processes essentially between quantum jumps now. So we'll have this quantum jump process, and we can repurpose our time evolution equation from before to this case and label it as a conditional probability of finding some observable value on our measurement. So what this describes is the decay in between two of these measurements. And the next step is essentially then to ask what happens to this equation if we modulate it by some prior measurement that occurs in between. And what we see is that on average, if you average over these measurements, it makes no difference. We obtain the same thing back. So what we obtain here is this independence of the average dynamics on measurements, and we then have a description in terms of a Markov chain of the thermalization process. So this has been previously conjectured and labeled the consistent histories approach. However, here we analytically derive it from the random matrix approach, or these chaotic wave functions.
Could you just more carefully explain the choice of observable, because that seems to be crucial for this? Because I mean, I can from experience, I mean, I can completely agree that like after some time scale, at least for some particular choices, then I could believe this to be true. But at short times, I mean, you know, it seems hard to believe.
Yeah, so at very short times, I mean, this will still work as long as it's in the exponential regime for short times. The choice of the observable is diagonal because essentially this gets rid of the oscillations that you'd see. Right. If it was off diagonal, what you'd see in this decay would be oscillations modulating the decay, and that's what when we're looking for a classical regime, these oscillations are typically indicative of quantumness. So we're restricting just to these diagonal parts because we're wanting to avoid these oscillating factors. So yeah, we have a description in terms of a Markov chain, and what I think is a nice way to understand this is in terms of if we instead of the fact that we have this measurement independence of the average dynamics allows us to think of these trajectories as hypothetical measurements describing the thermalization process. So we now have we can write our thermalization process in terms of these physical trajectories in the classical limit, or at least for these classical observables, we have what is a reasonable physical description of the unitary dynamics in terms of these trajectories. So to further expand on this approach to the classical regime, we'll make one more additional assumption to relate the system to the Ornstein-Uhlenbeck process. This OU process is defined by this equation, and it just gives a Brownian particle in our harmonic trap. So the key extra assumption we'll make essentially is that the system Hamiltonian now is harmonic. we have this harmonic dispersion, and it's here that we expect to see that the OU process should be recovered. And what we have now is we re-express our density of states in terms of some function beta. So I'm sure you can guess what that'll end up being. So and we now have the observable that's relevant is now this diagonal observable is essentially the position in this trap. So making the comparison then between what we would calculate from quantum chaos and what we obtain from the Ornstein-Uhlenbeck process is that we have the same decay to equilibrium, effectively zero for very large densities of states fluctuations. We have another fluctuation dissipation theorem essentially for the quantum fluctuations. That is I'll discuss in the next slide. And what I think is a very nice way to understand this is by making the comparison between the average over trajectories of the Ornstein-Uhlenbeck process and this average over measurements of the chaotic system. Coming back to these quantum fluctuations, we label this an Eigenstate equipartition theorem because what we essentially have relating the fluctuations to the right-hand side here is an equipartition theorem. However, we found before that this can be related also to this microcanonical variance, which again is a variance of an observable taken over the width of a single eigenstate. So what we relate here is that we have a kind of effective temperature over the width of individual eigenstates of the system. So each individual chaotic wave function can be seen to have its own effective temperature. And this kind of extends the intuition that we get from the ETH all the way into the classical regime. So just to summarize, we have this description in terms of random matrix theory and more generically in terms of the chaotic wave functions that gives us analytically, we can obtain the ETH and this description of the decay to equilibrium, as well as other quantities like fluctuations and things like that. So then we make the additional assumption looking at these just diagonal observables, and then it's also relying on the exponential decay. So here at this level, we require the Lorentzian shape of the functions lambda as well. This gives us this picture of consistent histories and the emergent description of the system in terms of a Markov chain. And at the final level, restricting ourselves again to the harmonic energy dispersion, we recover the results of the Ornstein-Uhlenbeck process. So we then have a description in terms of an effective Langevin equation of the OU process. We also have that this can apply to characterizations of quantum devices and other applications. So yeah, the last thing is that this I'll stress here that one of the lessons learned here is that this ETH intuition applies even at the classical limit, where we get eigenstate thermalization at the level of the equipartition theorem, which is so that the eigenstates themselves display a kind of equipartition theorem. So yeah, finally I'll thank Diego Porras, who I did this work with, and also Alexandra Elea Castro, who I'm working with now at UCL.